So today we're gonna continue with the study of induction, Faraday's law. The equation I introduced last class is written on the board. Faraday's law states that an induced EMF is equal to negative the number of turns in a coil multiplied by the rate of change of the magnetic flux. So the magnetic flux, the variable is this phi, and the rate of change means that the magnetic flux must change for an induced EMF and therefore an induced current to appear induced in a coil. Now the flux, the definition of flux is the same as electric flux. If you have an area and it's a bit slanted, you are going to draw the normal to the area, perpendicular to the plane. And in this case, we have the magnetic flux all the way from left to right. The angle between the flux and the normal is the angle theta that we're going to use for the magnetic flux. So the equation for magnetic flux is PA cosine. And the units are Webers. Okay? Tesla's meter square is the Weber. Now, there's a special case when the normal is parallel to the magnetic field. If the normal is parallel to the magnetic field, then the angle theta is 0. If the angle is 0, the cosine of 0 is 1. So the flux is just P times A. That's what we know as the maximum flux. When, let's say, all the magnetic field is going through the entirety of the area. There is no angle. There's no slanted angle. So the repercussion of Faraday's law is that you only get an induced electromotive force, basically an induced voltage, and an induced current when the magnetic flux is changing. If the magnetic flux is constant, like I showed you with a magnet last week, if you hold it still, then the flux won't change. So then there won't be any readings of current. No induction. And here. So the Faraday setup to explain the primary and secondary circuit, and to kind of explain this, here you have a coil, and you have a primary coil and a secondary coil. So the way this setup works is we plug the secondary coil to an ammeter, and we can plug this to a battery. So what we do is we move this, we place it inside the primary coil, right? So we get an induction, okay? Or we can do the other way around. We can plug this to the power supply, and there's a current here, and we plug this to the ammeter. And then we can introduce this, right? We can approach this towards this coil, and you will get an induced current here. The idea of induction comes from the change on flux. Remember, both of these can be modeled as solenoids. You have a bigger solenoid, a smaller solenoid when it comes to the cross-section. And if the current here is changing as you approach it towards this coil, then the magnetic field will change. That is going through here. Then the flux, which is measured by the amount of lines going through this cross-section, will change. as you approach it or as you move it, right? So that's the idea behind Faraday's law. Now, we're going to learn now why we have the negative sign. Okay? So, let's go back to the magnet sample. You have a magnet, north and south, and you have a coil like this. So if your coil here. So how do we determine the direction of the current induced by the magnet that is being moved towards the coil? So according to Lenz's law, which is basically what comes right after Faraday's law, the current induced in the coil will be opposite to whatever is producing it. So what the coil wants to do, the coil wants to do an opposite action to whatever is inducing the current. So the current is going to be induced here by the magnet moving towards the coil. So what the coil is going to try to do, the coil is going to try to repel the magnet. Now, to repel the magnet, this coil needs its own magnetic field. Why? Because then you have repulsion, right? So if you have a magnetic field, any object that has a magnetic field has two poles, the north and south. So the easy way to determine the direction of the current is by knowing the poles of the induced magnetic field on the coil. So basically, if that's north and south and it's going towards the coil, then the coil is going to induce a south and a north here. Why? Because then the south will repel the south. Okay, that's why. So if that's north and that's south, I can determine the direction of the current now. That will be the right-hand rule for coils or even solenoids. How do I determine the direction of the current for solenoids, for coils, if I know the poles using the right-hand rule? Easy. Your thumb, so this is the coil, right? Your thumb will give you the north. So if I put my fingers like this, the current is going like this. On out of the page here, well, in the perspective, right? Out of the page, and then at the bottom into the page. Out into. That way my thumb will point towards the left. So that's the right-hand rule for coils. So in this case, if that's the south and that's the north, I have to put my hand like this. Okay? So the current has to go out of the page, into the page, out of 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 the page, and then into a page, and then here out of the page. So it's out and into the page here, into. So it's like into a page, into a page, into a page, and then out page, out page. That's how we know. So then that way does a current. That way, that will be the north, that will be the south. That's the direction of the induced current. So that's how you determine the direction of the induced current. So that's why you have the negative. The reason we have the negative here is because the negative is telling you that the induced EMF and current in this case is going to be opposite to whatever action is producing it. Now, what will happen if I have the magnet here now? North and south, and now I'm pulling it away. What will happen in the coil? So let's draw a coil here again. So what will happen in that case? So the magnet is moving away now, right? This magnet here. The current inducing the coil by the changing magnetic flux is going to try to bring the magnet back. The opposite of going away is coming to you. So to attract the south, that's the south as the north. If I want to attract the south, this needs to induce a north here, and then the south will be there. Therefore, this will try to bring it towards the coil. If that's the north, that's the south, look what happens, right? It's just this. If that's my coil, that has to be the north, that's the south, there, right? So it will be into a page at the top, out of the page here, out of the page, into a page, out of the page. So you will draw it out of the page, into a page. Oh, wait. Oh, yeah. Right? So that's the way. Out of the page, into a page. Like that. Or, sorry, into a page here. Right? Into a page. And then out of the page like this. Like that, like that. You can put it like this. Out of the page, out of the page, out of the page. So the opposite of the other one. Like this. Okay? So let's go over this. All right, right-hand rule for coils and solenoids. This can be a singular coil, like looking like that, right? There can be many turns in here. All right. So if the current is going, you have to think in this like it's going like this towards the wall, okay? The current is going like this. Counterclockwise. All right, like this. Yeah. I want to use my 4 fingers and I want to trace the current. My thumb points upwards, right? So in that case, the north will be here, the south will be here. The magnetic field by that current is going to give you a magnetic field whose north is here, whose south is there. All right. That is the way you use that's the last right-hand rule, by the way. That's the way you use the right-hand rule for coils and for solenoids. Okay. So then now we can understand what happens when you open and close the switch, when you have a primary and secondary circuit, when you have a magnet and a coil, or when you even have just 2 coils. Okay, let's do an example. Let's show you an example of this. I'm going to give you a magnet north and south, and it's being dropped. So I drop the magnet, and I'm going to place a copper ring here. This is a copper ring. And the question is asking you, what's the direction of the current when the magnet goes through the ring? Okay, so what is the direction of the current of the induced current? Okay, the question is about when the magnet is here, right? So the magnet is here right now, and then what happens when it goes through? Let's practice what happens at this instance. When the magnet, this is north and this is south. When the magnet is dropped, since that's the north and that's the south, and the magnet is approaching the coil, as the magnet approaches the coil is going to try to repel it. So that's south, that's north. In this position, this will be the south, the north. So the coil is going to get a current induced where the south is here and the north is here. If the south is here and the north is here, what is the direction of the current here? So my thumb has to be here. So I'm going to do this. Like that. So the current is going to go clockwise. The current like that. I'll do this. Right? North and south. Now, what happens when the magnet has gone through? The magnet keeps going down because of gravity. Keeps going down all the way, right? So, in that case, let's just do this. I want to have the coil here. That's the coil, or the ring, sorry. And the magnet is here. Keeps pulling them. So the magnet is now falling, moving away from the ring. The ring is going to induce a field to try to bring the magnet back. If that's the north, that's the south. This will be the south, this will be the north. Because this attracts the north. So now my current will go on the opposite way, counterclockwise. Like that. Okay, that's how you determine directions for both the north and the south pole and the direction of the induced current. All right. Let's put this into practice now. is this equation there. Let's put in practice both Faraday's law and Lenz's law. Faraday's law is what gives you the value of the EMF. Lenz's law gives you the direction of the current induced. Both combined are basically the law of induction. Well, Faraday's law of induction, but both of them combined give you the full picture of the value and the direction of the induced current. Okay? So a typical example for this will be if we give you a coil like that, and then there is like several turns here, drawing like this. All right. So let's say you have 50 turns, rectangular turns. Okay, let's draw it like that so you can see there are several turns. 0.6 meters, 0.4 meters, and there's a magnetic field going through this rectangular coil. All right, so if the magnetic field is being reduced from 2.5 Teslas to 1.5 Teslas in 80 milliseconds. A, compute the magnitude of the EMF and B, find the magnitude and direction, find the magnitude of the induced current. Of the induced current. The only piece of information you need is that this wire has a resistance of 4 ohms. Okay, so you can see the question there. Now let's solve it. Okay, so here you are being given the initial field, the final field is into the page being reduced in 80 milliseconds, and they give you the dimensions of the rectangular coils. There are 50 terms. So what is the equation? but it asks us for the magnitude. So the EMF, which is the E, is absolute value, magnitude, negative N. Okay, how can you write delta flux over delta T? You can write it as flux final minus flux initial over time. Time is 80 milliseconds. Flux final. Flux final is P final area cosine of the angle. But wait a second now. What's the angle there? The field is into the page, perpendicular to the whole rectangle. So in that case, the angle is 0 degrees. So you just have to do P final.
Oh, I'm sorry. So does E give us the angle and we just put in the equation, right?
Huh?
Does the E on top of the flux final, does that give us like the angle that we're supposed to input for B final of A cosine of theta?
The angle comes from the direction. So.
All right.
So if the direction of the magnetic field is fully perpendicular to the area, then the angle is 0 degrees.
All right.
Okay. So it's just like electric fields. So if there's an angle, like if there's some slanted, right, then you have to look at the angle between the normal to the area and the field. But here the field is into a page. You see the X there? And then the area is basically the Y bone. So the field is going perpendicular, fully perpendicular to the plane of the coils. So that's why we use just B times area. All right. So then we have to do the calculation. Now, before you do the calculation, don't worry about even like B times the area, 0.6 times 0.4, right? The area is based on height. That's flux final. Flux initial is B initial times the area. So we know that's 1. B initial is 1.5. Area is... So why I say don't worry why? Because you can do E equals to the absolute value, negative 50, and then here you multiply 2.5 times 0.24 like that, minus 1.5 times 0.24, right? And then you divide all this. Now, delta T is 80 milliseconds, which is 80 times 10 to a negative 3. And then you close this. Do that. All right. So 2.5 minus 1.5 is 1. That's 0.24 over 80 times 1,000 and then times 50. So we're going to get, and then by the way, because I'm taking the magnitude, that is, the minus is goes away. So you get 0.24 times 1,000 divided by 80 multiplied by 50. The 50 multiplies. So that is equal to, you see, the time is very small. So that will give you a large value. 150. 150, the units for E are volts. Not bad, kind of realistic there. All right. So that's the answer for part A. 150 volts. Okay. So as long as you keep it organized, the right units, then it's easy to work these questions. That's part A. Part B is asking you to find the current, the value, and the direction. Let's find the value first. So, part B, to find the value of the current in use, you're going to use Ohm's law, which is the E divided by R. E is 150. R is the resistance 4. That will be 37.5 amperes. That's the value of the current. All right. Now the direction. For the direction, we're going to go back to this. And we have to read the problem. It says that the field is being reduced. So the magnetic field is being reduced, meaning that the current induced in that coil has to oppose that. Sort of like a magnetic example, right? If you bring it towards the coil, if you push it away. So in this case, the field is being reduced, and the field is going into the page. What's the opposite of reducing something? Increasing it, right? So you want to increase the amount of field. That current induced, that current there, wants to increase the field that is being reduced into the page. So this current will increase and into the page field. So my current has to flow, so the north points towards the board like this. So if I do this, what happens? So the current goes clockwise. A clockwise current if you feel increasing into the page. So the direction for the current will be clockwise. All right. That's an application of Faraday's law and how to determine the direction of the currents. Okay. Any questions about that? So my suggestion will be that you practice this, practice your right-hand rules. I want to post today a summary of the right-hand rules, okay? This Thursday, we're going to finish with all the topics for the exam between Wednesday and Thursday. And then on Thursday, I'll give you guys the second exam to take home and bring it next week. So make sure you come to class on Thursday to finish with whatever topics and then to hand in you guys the second exam. All right. The second exam will be done in paper, but you will take it home to work it in the weekend. And then we will start changing topics next week. Next week, we'll start gonna go into radiation, optics, and other applications. Okay. All right. So how do we apply action? I talk about electric guitars, speakers. So the basic applications for induced current are basically light, to provide power, to turn on light bulbs or LEDs. Okay, there's this whole experiment that you can do at home, DIY experiments or projects that you can find online, where you can build your own metal detector. That's a bit tricky to do, but you can do it. But the easy one for it will be the Faraday flashlight. So the Faraday flashlight is a device that uses a coil, sort of like this. So you can place a magnet inside one of these, and you can plug this to an LED. And then when you check it, you check the magnet inside the coil, because the magnet, remember, the coil is not being powered now. So I'm leaving the coil like this, and then the magnet inside, like this. I place the magnet inside, and then I can check it. And as you check it, you can turn on and off an LED. Okay. So how does that work? How does, like, what will be a simple case for? The simple case will be the motional EMF. So let's show you that now. And the motional EMF, guys, there are a couple of questions about that in the assignment. It's very easy. The formula is easy. I want to go over the theory behind it, because then we're going to use that idea for generators and motors, which is basically the other application of Faraday's law. The motional EMFs. In this one, you have a few conducting rails, like that, like this. And then at this one here, you have like a light bulb here, like this. And then you still have these conducting rails, of course. And then on top of the rails, we place a metal bar. Okay. So the idea is that we are going to apply this metal bar here. You're going to apply a force. We call this a force apply. And hey, you see that there is a force in there. So you will expect the bar to accelerate. But the experiment is going to be done in such a way that the speed of the bar is constant. How? Because This is gonna be done in a region where there is a magnetic field. So inside this region, there is a field into the page. In this case, it can be out of the page. I'm just gonna put it into the page right now. Okay, like that. And let's extend this as well. Okay. So how does the motion of this bar, so moving it like that, how does this trigger this? Like turns on the light bulb. Turn on the light bulb, you need some sort of electric power. So there needs to be a current being induced in this cell as well. Sort of like in this case. So as the bar moves from left to right, it's gonna move certain distance. So after some time, the bar is going from here to here, and it has moved some delta x in certain time. As the bar moves from left to right, it's covering, is sweeping some area, right? There's some area that is being swept in here. And that's what we need, because the EMF, the magnitude is the absolute value of negative and rate of change of flux. Now, for the bar, or just the bar, the N is 1. Right? So it's just 1 bar. So this is just 1. What about the rate of change of flux? So flux, you remember, is B area again cosine theta. Well, let's take a look. The magnetic field is into a page, and the bar is like this. So the angle is 90 degrees. Sorry. The magnetic field is completely perpendicular to the bar. So that means that the flux is just P times the area. All right, what area? This area. Okay. Now I need to know the length of the bar. So let's suppose the bar has some length L. So this is just 1. This is just B. The area is base times height. And delta x as the area. So I can put in the equation absolute value of negative L delta x, or sorry, B times area like that. B is constant, so it comes out. L is constant. And then you have delta x over delta t. That's speed. So this will be speed. So that's your EMF induced. The EMF induced by the motional EMF is magnetic field, length of the bar, times the speed. That is the equation for the EMF. Okay. So that's very useful because now I can also find the induced current. If I assume that the light bulb has some resistance R and it's ohmic, the current induces VLV divided by R. Okay, so what about the direction of the induced current? Remember, Lenz's law still applies. So the bar, there are two ways you can understand this. The force applied is acting towards the right. And the speed is constant. This V is constant. The only way the speed can be constant is if there's no acceleration. So the force, the magnetic force, because there is an applied force, there has to be magnetic force, has to be in opposite direction. But let's suppose you don't think about magnetic forces. Then we have to go back to Lenz's law. What does Lenz's law tell us? Whatever is producing the EMF, the current, is opposite to whatever is producing it. If the force is towards the right, there has to be an opposite force towards the left. That opposite force is the magnetic force. That's the magnetic force. Okay, so we have to go back to right-hand rule again. The magnetic force is towards the left, and the field is into the page. So force, field into a page, current, field, force, right? Remember that magnetic force is ILB sine theta. So my current has to be upwards. So as it goes like this, current, current, current. So my goes counterclockwise. That's your current induced. That's the current powering up the light bulb. The direction of the current, that's the value of it. So what other things can I find in the motional EMF? I can find the applied force or magnetic. The applied force is equal to the magnetic force. So the force applied is equal to the magnetic force is equal to ILB sine of 90. The angle between the field and the current is 90 degrees. So I L B. So A square, L square, B divided by A. Current, force, apply a magnetic. Now, ideally, there's no friction. You are basically doing mechanical work with a force applied. You are doing mechanical work to turn on this light bulb. So ideally, all the mechanical work has to be transferred into electrical energy. So let's check if that's true. Let's find the mechanical power and the electrical power. Start with the easy one. Power electric. The electric power, that's Ohm's law. I can use the equation I square R. Remember we did that in chapter 17? So that's the current square times R. So I get the equation here. This is the electrical power. What about the mechanical power? So I hope you remember this from physics 1. When the speed is constant, mechanical power is equal to force applied or force times speed or force times velocity. That's the force, right? Square, L square, V divided by R, times V. I get V square, L square, V square divided by R. So this equation is the same as this. What I just show you guys is that the mechanical power is identically, in theory, to the electrical power. Is that always the case? Not really. We are ignoring friction. We are ignoring heat. We're basically ignoring the first law of thermodynamics. Space here. Here. The first law of thermodynamics states that the energy provided, heat, right, is equal to the work done or by the system plus the internal energy of the system. So there's always some sort of energy that is being lost in terms of internal energy. Not all the energy provided to a system is going to be the work. That's only in adiabatic cases. So what we're ignoring here, we're ignoring friction or any other sources of energy where this energy may be escaping. So not all the mechanical energy goes into electrical energy. An application of this that you can find online is when people, by riding their bicycles, they turn on their flashlights in front of the bicycles. One experiment I used to do with students in school was to use manivelles to charge mobile phones. You can connect the end of a manivelle to the cables that go into the USB and then plug into your phone. The problem was that the amount of energy you had to input, that means the amount of power you had to use to make it work, was more than the output. So you are giving more energy than the output. That's the whole, I don't know if you have heard about that. That's one of the sort of issues, right? That not all the energy that we input is usable, right? That's the whole idea behind efficiency of machines, right? If you kind of talk about thermal machines in thermodynamics as part of the second law of thermodynamics, which is not to be the first law, okay? In thermal machines, we introduce a hot spot, a cold spot, and then how some of the energy is wasted and how the efficiency of machines is never 100%. Here, we're assuming that the efficiency is 100%. And that's not always the case. However, it's a good math exercise to see that in theory, if everything was ideal, all the energy provided by the mechanical force goes into electrical force. That's the idea behind, or that's one of the applications of Faraday's law. Okay. So let's do a couple of examples. All right. Let's do a few examples on this. Okay. So I know there are some examples in web assign, but I'll use one that I have here, which is similar to the one that you have in assignment anyway. Yeah, this way. Okay. So let's erase all this. So the equations for this, right? These two are the main equations. These ones are X equations, the power and the force, but they still have them written down just in case you may need them. Okay. So we've used all this already. So the question I have here is now with a resistor. You have again the conducting rails, but here you have a resistor like that. You have out of the page that magnetic field, and you have a bar at the end of this rail, or here. Right. And they show you the force applied. So the bar is moving. But the length of the bar is 1.40 meters. The resistance is of 4 ohms. The field is of 2.20 Teslas. Oh, sorry, 1.6. Let's see this. It's 1.6, 1.60. And they ask you to find the force, so you want to find this. If the speed is 6 meters per second. All right. Okay. So the equation for force, so let's put here A. What is the value of the force? Um, The equation, remember, for E is PLV. That's in the equation sheet as well. The current is just PLV divided by R. The equation for force, magnetic or applied, is P squared L squared V divided by R, right? ILB. ILB. If the angle is 90 degrees. So we need this equation. The force, we want to find the force. P is B squared times L squared times the speed divided by the resistance R equals to 4. That's it. Application of formula there. So that will be 2.2 squared 1.6 squared times 6 divided by 4, 18.6 newtons. That will be question A. Question B is find the direction of the current. So that's another question there. So B, what is the direction of the induced current? Okay, so by Lenz's law, if the force applied is to the right, the magnetic force must be pointed towards the left. That should be my magnetic force. So apply force vector to the right, magnetic force vector to the left. The field is towards you, out of the page. So field out of the page, and like this, right? Right? Magnetic force, field. So current, field, force. I'm using right-hand rule for forces there. Okay? So my current has to go down. Left. Up. Right. So that is clockwise. The direction of the current has to be clockwise. All right? And then question C. Find the value of the current. Like this. So B and B divided by R. B L V divided by R. So that will be B L V divided by 4. Right? BLV divided by 4. So 2.2 times 1.6 times 6 divided by 4, 5.3 amperes. Sorry. Okay, so that's how you find again current and direction. It's a very simple application. All right, it's probably not the most commonly used, but I give you an idea again on how we relate mechanical power or energy to electrical power. Okay, it already gives you that idea how you can produce that. I think I mentioned in class last week that applications for this are for generators such as hydroelectric dams. I mean, you have seen waterfalls. Maybe the best example around here would be the Niagara Falls, right? Where normally we take advantage of those by placing generators at the bottom of the falls. Things that are much bigger than this. But at the end of the day, what happens is all the potential that is converted into kinetic energy at the bottom, all that energy is then used to power up the generators, to basically induce or produce alternate currents. All the current that we get in our households are alternate forms of current. And you're going to learn a little bit about that today. Because the second application, you see like the current here was kind of constant, right? The magnetic field was constant, the speed. So it's kind of a simplistic scenario. But how about currents and voltages that change over time, which are more realistic, okay? So that's what we're gonna get now. And for that, I have to use the slides because it can be, at least to show you the diagram. Yeah, it's here. By the way, guys, when you go to slides, you can find the bar, Lenz's law, what we talk about today, you know, the EMF, the force, mechanical, electrical power, is all in that. Okay.
Oh, sorry, I wanted to ask, when I wanted to look back at a past video for like another day, it asks for a password. Do you know what that password is, or does it say it like in
the announcement? So if you go to do I have it here?
Oh, so you write the password in the announcement?
Yeah.
All right.
So normally the way I do it is I post the link. For example, last class, right? Last Wednesday. And the password is that.
All right, thank you.
Okay. Okay. This is what I'm talking about. So what do we have here? Here we have, again, a light bulb that will be your output. You have, you know, a more complicated, more complex sort of situation or setup about rectangular loop now. So it's not just a bar. You have the manivelle, that's the mechanical input. So now you're not pushing it or pulling it. Now you are rotating it. This W, I hope you guys remember, is your angular speed. Or if it's a vector, angular velocity. That's your magnet there, north and south. And this should remind you what we talk about in torque. So there is actually a relationship because the magnet gives you constant magnetic field. And that, even though we're making it rotate, right? There's also a torque you can measure due to the rotation. Okay, so what I mean by Faraday's law and the angle, right? you have to draw let's see if I can find the right color. Yeah. We're gonna draw this. What I just drew there, sort of there, right? I'm gonna make it bigger so you can see like that, like that. That red line I drew is the normal to this rectangular loop. Okay, so that will be the free. Oh, this one. Yeah, that's the normal. The field is going from the north to south, and it's making an angle of theta. So that's the angle. So no, it's not 90 degrees, guys. But wait a second, though. This loop is rotating. So the angle theta will not be constant. So here are a few factors that you need to remember always for induction. If you want to induce current, the flux depends on magnetic field, depends on the area and the cosine of the angle. If the magnetic field is constant, the area or the angle must change. In the motional EMF, the area was changing, right? As you were moving the bar. In some cases, the magnetic field, like in the example that we did before, right? The magnetic field being reduced. In that case, the field is changing. But here, the field is constant. This is the magnet. This is always constant. This is constant, and the area is constant. So what else can change? The angle. This angle, theta, is the one changing. Why? Because as you rotate it, the angle between the normal and the flux, and the magnetic field will change. And why does it change? Because of this. In circular motion, does anybody remember what's the value of W? We're going to assume that it's a constant rate.
Constant rate circular motion, would it be centripetal, right?
Yeah, there's centripetal force. But what's the value of W in terms of, yeah, what's W? What's the equation for W in a constant circular motion? Anybody remembers? Why? So W is delta theta.
Oh, delta, the little circle over the over time, right?
Over time. Yeah. It's the same equation as constant motion, linear, but now it's circular. So the value of the angle depends on the W on this. You can say that delta theta is W delta T. That's how your W is going to play into account. But you can see that it's not going to be constant though. So now we're going to apply Faraday's law. Faraday's law is negative n, well, the magnitude, absolute value of negative n is the number of turns of this. This is one loop. It can be many loops, by the way. So n is still there. Change on flux, the rate of change on flux, right? Flux will be the magnetic field, the area, which are constants, multiplied by the cosine. Oh, what do I do here? Okay. My bad. by the cosine of delta theta. But that's all divided by delta t, right? Oh, yeah, there's an n here. So that's the equation almost there. N times B times area times this. So how can we do this? We have cosine in between. Well, let's show you on the whiteboard that will be easier to do there. So you already saw almost how the equation is gonna look for the generator. So for the generator, the EMF induces the magnitude NBA cosine of delta theta over delta t. So to do this, guys, we have to do this. We have to do NBA d cosine theta respect of time. You have to use the derivative of that. So now remember, theta is omega t. So derivative of cosine, still have this by the way, is negative sine of omega t. Derivative of this is negative, negative, positive, n, p, a, w, sine omega t. That is your EMF for a generator that you are rotating at constant angular speed. Eventually, we call W in generators, we call W angular frequency. We're gonna use this in labs, by the way. Okay. Why do we call it like that? Because for a generator, electrical generator, for example, wave generator, normally we get frequencies in hertz. So your W, your angular frequency is 2 pi f, where f is the frequency in hertz, the inverse of period. So that's the equation. And then if I plot, the other one was just constant. But now I can plot this guy as a function of time. If I do that, right, if I plot this, I get E here in volts, and I get this. Where the amplitude is the maximum E. The maximum E is the amplitude of this sine wave, sine function. Number of turns, magnetic field, area, angular frequency. That's it. And the period, 2 pi over omega, or 2 pi over W. That's the period of the wave. So that is a more realistic, in fact, that is actually the type of voltages that we get in households. On Wednesday, is tomorrow we're gonna do inductors. But on Wednesday, we are going to be working with AC. We're going to introduce and finish on Thursday. Thursday is going to be a short class, by the way, guys. Very short, because I'm going to finish with that, and then I'm going to give you the exam, and then you're going to start working on it. All right? But we're going to finish with
when is the exam again?
Huh?
When is the exam again?
On Thursday. I want to give it to you guys on Thursday. All right?
Oh, okay.
When we all finish with all this, with all the topics of magnetism. So that is the type of voltage that you get when you use a generator. Okay. A few other things that you can find is the torque, right? And actually I can show you. Well, here. That's it, right? That's the equation there for a rotating coil. And an electric motor, we take into account the forces. Remember that? You just remember from torque, one going up, the other one going down. All right. So in this case, the torque, you remember the equation is NBI sine theta times area, right? So in that case, the sine of theta is the angle that I just introduced in this case for the generator. All right. There's an example on this. And then I introduce a little bit of inductors. We're getting to the point where we can start using coils in circuits. You see, you're talking about electricity, you're talking about voltage in the coil, EMF induced in the coil. So those are all the ingredients that you need to actually start using coils in circuits. Sort of what we did with capacitors, right? But let's one example on this, show you all the variations you can get. And then tomorrow we'll do inductors, everything up until circuits. Guys, assignment 7 and 8, you should be working on those already. 9 and 10 are the assignments to finish these topics, all right? They are due in August, so they're still due. You still have like a couple of weeks. But try to work on those. So then when you do the exam, you don't have to worry about that. This one, I think, is assignment 9. Okay. So we're going to do an AC generator example, all right? With a few variables in there. Okay. An AC generator. So the problem tells you that we have an AC generator. All right. It has 12 turns. Okay. With a cross section or with area, A equals to 0.080 meters squared. All right. And resistance of 12 volts. The coil, so this the coil rotates in a 0.50 Tesla's magnetic field. Okay? At a frequency of 60 hertz. At a frequency of 60 hertz. So a few questions here. First, you're going to find the maximum EMF induced by this AC generator. Okay. So as you can read in there, the AC generator has 12 turns with this area inside this magnetic field at this frequency. So what is my equation for the Emax? Number of turns, magnetic field, area, W. Or is that right? Now, number of turns is 12 turns. Magnetic field is 0.50. Area is 0.080. And W. So how do I find W? W is the angular frequency. My frequency is 60 hertz. So W, remember, is 2 pi times 60. Don't forget that, please. Okay? So it's 120 pi. Perfect. So the EMF is 12 parenthesis 0.50 0.080 times 120 pi. All right. So that's how you find the 181 volts. Part B, find maximum current. So part B, find the maximum induced current. I induce max is the maximum EMF divided by the resistance 12. So around 50 amperes. Yeah, right? There you are. Part C. Find the EMF as a function of time. Well, that's easy. The EMF is Emax times the sine of omega t. That's why it's function of time. That'll be 181 sine W 120 pi time. So that's how you find, that's basically your voltage, the equation, right? Faraday, find the maximum torque. Find the maximum torque necessary for this coil to turn. See, we already know that's 181, so let's erase this now. Faraday, compute the maximum torque. Torque max. Let's not forget the equation for torque. Magnetic torque. NIAB sine theta. The maximum torque will be when theta is 90 degrees. Yeah. So N is 12. We need the maximum current, 15 amperes. The area, 0.080. The magnetic field, 0.50. There you are. Right? So that's how you do it. So 12 times 15 is 180 times 0.08 times, not a lot, only 7.2 newtons meters. Yeah. And part E is actually very important, all right? In part, you want to find time. You see the variable time, you haven't really used it, but want to find time, and this can be different type of question, like different situations, but we want to find the time when the coil reaches half of the maximum value. So, here. Find the time when the E as a function of time is equal to half of E max. Okay. So we know E max is 181. And we know this. You did this in, that's one, right? So that's the E as a function of. We want this to be half of this. So in here, right, you're gonna do E max divided by 2 equals to this. Now, E max is, well, 181. So that cancels. That cancels. And you get that 1/2 equals to sine of 120. That. So this is what you need to remember for this part. You're going to solve that trigonometric equation, keeping in mind that you have W as 120 pi. So the angle that you're going to compute or that you're going to find is not in degrees, but it's in radians. So when you take the sine inverse here, okay, sine inverse of 1/2 equals to sine inverse of this equals to this. This, because of this, the argument of sine is in radians. So this angle has to be in radians. The sine inverse 1/2, guys, let's do a small refresh, you guys. I should remember from math. The sine inverse of 1/2, if you use a calculator, it will give you 30 degrees. But how do I go from 30 degrees to that? I know it's pi over 6 because one circumference is equal to 2 pi radians. You may want to write this down. And one circumference is 360 degrees, is 2 pi radians. So 180 degrees is equivalent to pi radians. So if you say that this is 30 degrees, to convert to radians, you multiply by pi over 180. The angle in degrees is pi over 180. That's how it is pi over 6. So this is pi over 6. That's equal to 120 pi times time. So that makes it easy. Now you can cancel pi's. And then you get the time. Time will be 1 over 6 times 120, which is 1 over 720 seconds. If I were to round that in milliseconds, that's 1.39. And I know what you're thinking, though. You know how you are rotating, right? Because you keep rotating, it's a AC generator. That's not unique. You probably remember this from trigonometry, but 30 degrees is just the main solution, the first quadrant. The other solution will be in the second quadrant. which will be 5 pi over 6. So 5 pi over 6 also but just focus on the main one, all right? In here, unless they ask you. There's a general solution for that, but I'm just taking the first solution, all right? So that's an extra type of question that requires some math. You may get it. It's in Cengage as well, similar. But that's AC generators, guys. Okay, so that's good. We are about to start inductors. So I will leave that for next class or tomorrow. All right. So tomorrow we're going to be doing a few more examples of this. We're going to finish with inductors, inductance, and circuits. And then on Wednesday, we'll do everything related to AC circuits. All right. Okay. So I already graded the quizzes. I'm in the process of finishing grading labs. If you have anything past due, please complete it. Okay, finish it. I'm gonna be updating assignment grades. But I think everybody has finished this one, right? If you haven't taken test 1, please come tomorrow at 10 a.m. All right? You need to take test 1 before test 2. So you have tomorrow, Wednesday, and Wednesday to do that, all right? And then you have to make up labs. I'm going to be here tomorrow at 10 to help you guys making up any missing labs. Even if it's not your lab day, come so you can use that time as for your advantage, okay? And I'm going to be updating homework grades 6, 7, 8 as you go, all right? Any question before we finish class?